Well, thank you very much, Marlene and Graham, and it's a pleasure to speak to you all today. As Marlene said, I lead a Centre for Doctoral Training in Cambridge on the application of AI to the study of environmental risks that actually is jointly between the University of Cambridge and the British Antarctic Survey. And so much of what I'm going to talk to you today about is some pieces of work that the students who are part of or associated with that Centre for Doctoral Training are working on. Just a disclaimer at the start, I'm a climate scientist by background, and so most of the machine learning expertise that's involved in these projects come from the students themselves or their co-supervisors rather than from me, so I can't take much credit for the details of the machine learning elements of it. So I just thought I'd start off with the sort of, if you like, the high level picture around all of this, which is that on the one hand, there is an increasing need for what you might call actionable information on climate related risk. And by actionable, I mean information that is easily usable for decision making. And in many cases, that means well, first of all, means increasingly a need for information at a local level rather than just at a global level in terms of climate-related risks, but also, and I'll come on to this at the end of my presentation, also increasingly going beyond meteorological variables and understanding how those meteorological weather and climate hazards translate through into risks associated with businesses, or risks associated with health, or risks associated with the increased risk of conflict or migration and so forth. And so seeing this as being a pipeline, and a need for a pipeline going from the climate related risks into those, if you like, socio-economic related risks. So that's where there's a need. Where there's an opportunity is that we have ever increasing amounts of data, really vast data now coming from a huge diversity of sources in terms of our changing environment. And some of that is from remote sensing, from satellites, increasingly from network sensors on the ground, from ever vast volumes of data coming from computer simulations. And so the challenge is, can we take advantage of advances in terms of machine learning and other data-driven techniques in order to bring these things together, to utilize those vast data sets to better inform decision-making associated with climate. So what I'm going to do, if I can get to the next slide, let's see. There we go. What I'm going to do today is I'm going to talk through 4 different examples where we've been working applying different machine learning related approaches to different types of forecasts in the weather and climate space. So the first example that I'm going to, and actually I should say that not only are these different physical situations, they also are employing very different types of machine learning or data-driven approaches, just to give you a sense of the scale of the different opportunities. And of course, over the course of the next 3 days, you're going to be hearing so many more different elements of this. The first example I'm going to give you is around looking at sea ice and looking at how we can use data-driven approaches to forecast over a seasonal timescale the future evolution of, in particular, Arctic sea ice. I'm going to give you an example in terms of looking at temperature extremes, in particular heat waves, and in that instance, how we can combine together past historical observations together with climate simulations to improve forecasts of extreme weather events such as heat waves. In terms of ocean forecasts, I'm going to give you an example where we've been looking at the interpretability question associated with data-driven approaches and exploring the physical basis for data-driven models. And then finally, I'll talk very briefly about some work that we've been doing, looking at how we might be able to look at machine learning approaches to hydrological forecasting. So let's take the sea ice example first of all. And again, it's being a bit slow. Here we go. There we go. Right. So let me talk to you a little bit about seasonal sea ice forecasting. So first of all, just a bit of background in terms of, what are we wanting to forecast? Why is this interesting and why is it important? Arctic sea ice has a very strong seasonal cycle to it. It sees significant melting over the summer months, so that Arctic sea ice reaches its minimum extent each year in September. And the graph that you can see there shows over the satellite record, so since 1979, that decrease in the amount of Arctic sea ice that has been observed over the last 4 decades. And you can see a really precipitous decline. In September, sea ice extent is now half what it was at the start of that satellite record. Now, there are physics-based dynamical models of that sea ice evolution, and there are also simple statistical forecasts that are currently used to look at the evolution, particularly looking at that seasonal evolution of sea ice. But the question is, could we be enhancing and improving those forecasts using more data-driven approaches, machine learning-based approaches? So the goal of this is to look to see whether or not we can forecast sea ice over the next 6 months using a data-driven deep learning approach. And this is important because that seasonal evolution of the sea ice potentially has important implications for weather systems across the northern hemisphere. It's thought that there are essentially teleconnections between what happens in terms of that Arctic sea ice and then the knock-on effect throughout northern hemisphere weather. And might also be useful for ecosystem management. Again, that seasonal evolution of the sea ice has really important consequences in terms of a lot of the ecology of that Arctic region. And if you're looking at intervening in terms of conservation work, then having an understanding of that seasonal forecast in terms of the sea ice is really important. So what the approach that we've been using here to try and develop a data-driven deep learning approach is to bring together slices of climate-related information, both the satellite observations of sea ice, together with meteorological information, and treat each of those as being analogous to two-dimensional images that we can then input into a convolutional neural network. And so if I, on the next slide here, give you a little bit of a sense of how this is working. So we have sea ice concentration. We have 11 different climate-related variables, and we have a very simplistic statistical sea ice forecast, just a linear trend in terms of that. And we use that as input into an ensemble of UNet networks. And the way that we treat this is essentially as a classification task. So what we're wanting to do is to classify whether or not we have open water, in which case that's characterized as a very small sea ice concentration, so less than 15% sea ice concentration, marginal sea ice, which is in between 15% and 80% sea ice concentration, or full ice, which is over 80% sea ice concentration. And so what we do is we have an approach where we have a feature extracting encoding path that downsamples the input data, and then a decoding path that upsamples the data. We train everything, so we only have a certain amount of observational data, but we also have climate model simulations. And so in order to expand the amount of data that we have to help to train this model, we pre-train everything with some very large climate model simulation data from the CMIP6 database. And then, having pre-trained the model, we then use the observational data from 1979 to 2011 to train the model, validate it on the next 5 years, and then test it on the most recent 2 years. And the output of all of this is a future 6-month forecast with those 3 different classes of sea ice, the open water, marginal ice, and full ice extent. So here's just some results of where we performed this. And we're looking at comparing it against the existing forecasting techniques, which are either the full dynamical physics-based forecast or a very simple linear trend, which is one of the things that's actually input into this data-driven approach as well. And so what you see in the top figure on the left is the data-driven approach in blue, the UNET derived technique, together with the dynamical physics-based model in red, and then the linear trend in grey. And this is a skill score that you're seeing being plotted here. And at all the different lead times, which is the looking at 1 month, 2 month, 3 month, 4 month, and the full 6 month forecasts, then you can see that except at the very nearest time, where the dynamical physics-based model still slightly outperforms the data-driven model, at all other lead times, then the data-driven model is exceeding the physics-based model or the simplistic statistical model. The actual results that we have in terms of 2020, when we were running this model, looking at the comparison between the actual observed sea ice extent and the sea ice extent that was predicted at different lead times associated with this data-driven approach. So, we've developed this approach that does appear to have a significant skill and increased skill compared to existing techniques. So that's the first example I wanted to give you. Second example, and this is an entirely different approach, and this is looking at heat wave forecasts. And it's one example where we are particularly trying to look at the projections of climate-related extremes, particularly at a local level, because this is something that is critically important in terms of decision-making, as I was describing at the start. So the goal here is to generate city-scale projections of extreme temperature, and this is the approach that we're wanting to use is by post-processing climate model simulation at specific locations, so that we can then use the output in terms of decision-making. And I've described here some of the sorts of sorts of impacts, socioeconomic impacts that those extreme weather events are likely to have, or extreme temperature heat waves are likely to have, in terms of labour productivity, the impacts on infrastructure, transport, and significantly on mortality. Now, the challenge here is, first of all, that the raw output from climate models has significant errors with respect, and often systematic errors associated with it. And the little sort of postage stamps images that you can see on the bottom left here are from actually I think these are from CMIP5, but they're a set of climate model simulations, different climate models, and you can see that at a regional level, there's significant differences between the different climate models. And so if you're looking at a regional, local, especially city scale, you need to employ some bias correction onto those models, but doing so in a way that is sensitive to extremes needs some careful attention. And so what we have here in terms of input is we have these raw climate model forecasts, but we also have historical data from observations. And what we're wanting to do is look to see how we can combine the two, how we can use those historical informations to bias correct the climate models, and in such a way that we are sensitive to the extremes and therefore create better projections of future extremes. So if I just go to the next slide. Here we go. So the approach here is to use the past, where we have observational data, to learn the statistical relationship between the climate model output and the observational data, and then to apply that to the future climate model simulations. But so that we are sensitive to the extremes, we look at the probability distribution of in terms of temperature, and we look at bias correcting each different quantile associated with that distribution separately, so that we are being sensitive to the way in which we treat the extremes. And we also, because often the biases have a seasonal dependency associated with them, we undertake that bias correction in a seasonally evolving way. And so what you can see on the bottom row here, on the left-hand side, is focused in on looking at one particular location. We happen to have chosen Chicago to look at here. And what you can see is over the period 1980 to 2019, in blue, for the summer months, June, July, and August, you see the distribution of maximum daily temperature. And in red, you see the output, same distribution, same time period from one particular climate model. And you can see the difference between the two. And the middle panel is where we've been using this quantile mapping approach to bias correct the future climate model forecasts using that historical time period. And then finally, on the right-hand side is where we've then been focused in on looking at the increased risk over the next 40 years in terms of extreme weather events. And so the different curves are looking at the likelihood of, in one case, exceeding 25 degrees centigrade, and in another case, exceeding 30 degrees centigrade over summer in the future. So this is quite a simplistic approach, and the question is, can we extend this still further to bring in some machine learning? And so what we're looking at is, instead of explicitly calculating the bias at each quantile for each month, as I was just describing, can we essentially learn the function that maps between that observational and the climate model data? And we've been looking at different approaches in order to be able to do that, one of which is using Gaussian process approach, and that's what's shown here, where we compared against the basic quantile mapping that I was just describing, with using a Gaussian process-based approach to learn that relationship between the historical data and the climate models. And there are indications that indeed a machine learning approach does an even better job of looking at the extremes and is more skillful than just looking at the traditional quantile mapping approach. So there's certainly more for us to do here in terms of refining this, but the indications are that there are significant opportunities for making advances, integrating machine learning techniques into this sort of bias correction and downscaling approach. And one of the challenges now is to try and understand how we can develop the most computationally efficient processes in order to do that. So the next example, third example that I want to go through is work that we've been doing in the oceanographic context. And again, this is looking at a very different style of problem, a different way of using machine learning approaches to access a different aspect of the forecasting problem. What we're looking at here is really looking at interpretability of data-driven approaches. So what we've been doing here is taking a very simple oceanographic model. This is a simple representation of the Southern Ocean, which contains the key dynamical processes associated with the Southern Ocean circulation. So if you look at the image on the top right there, it's a schematic of what happens in terms of the Southern Ocean circulation. So the overarching circulation in the Southern Ocean on this schematic, Antarctica is on the left-hand side, and the ocean coming in, for example, from the North Atlantic is on the right-hand side. And what you have in the Southern Ocean is, first of all, very strong winds that blow across the surface of the ocean around Antarctica. And those very strong winds, as they drive against the surface of the ocean down to the Coriolis effect, they help to drive a circulation that's perpendicular to the winds. And that, together with the surface buoyancy forcing, so the temperature and salinity forcing, helps to drive the overturning circulation of the Southern Ocean. And you can see that schematically in this figure, where you have this upwelling of water around Antarctica that then branches into two directions, and some of it then sinks down around the coast of Antarctica, forms Antarctic bottom water, and the rest of it sinks down and travels back up towards the North Atlantic. So that's the overturning circulation. It's quite complex how all the different dynamical processes interact with each other. Not only is it the wind-driven circulation that's important in creating the balance associated with this, but also a competing eddy-driven circulation. So you have associated with those strong winds that are blowing across Antarctica and with the density profile that's set up in terms of the ocean, a very strong current that circulates in the ocean around Antarctica, the Antarctic Circumpolar Current, and eddies that are associated with that are also important in terms of driving the circulation. So complex set of physics that are encapsulated, and are encapsulated even within the very simple model of the Southern Ocean that we've been investigating. So the simplified version of a Southern Ocean model is shown on the left-hand side here, and it's literally essentially a channel model. So what comes in the left-hand side goes through to the right-hand side again, and then back into the left-hand side. But it's not quite a channel model, because what we've got is a significant amount of that channel is blocked off on the right-hand side by the equivalent of South America. So this is a very simplified version of South America, and there's a very simplified version of Drake Passage, which is essentially a ridge at the bottom of our simplified South America, which the water in this model has to flow over. So that's the setup that we have. And what we're looking at is literally just how that simplified ocean evolves over the course of a day, and in particular how the temperature profile evolves over the course of a day. And what you see on the sort of middle panel, if you like, in the blue and red, is how that temperature in the simplified model has changed over the course of the day. And if you look at the bottom panels of these, which are a cross-section through depth of this model, you can see these red zones at the top and the bottom, at the very south and at the very north of that plot. And those red zones are predominantly the change in temperature which is associated with the overturning circulation that I just described. So that's all the physics. And the question is, can we, instead of having a physics-based model of this complex system, can we look to be generating a data-driven model? And will that data-driven model represent in some way some of these physical processes? So the goal here is to predict daily mean change in ocean temperature for a single grid cell based on the variables at surrounding locations at the current time step. And what we're wanting to do is, within that, assess the physical basis of the data-driven approach. So what we've been doing is looking at a very simple linear regressor, where the inputs are temperature, salinity, the velocities in all directions, the eddy related bolus velocities, which are, in the simplified model, all those eddy processes are parameterized by something called the Gent-McWilliams parameterization. Sea surface height, latitude, longitude, depth, and also the second order polynomials of all, between each of these different terms. And all those trained by minimizing least squared errors with ridge regularization. And what you see on the right-hand side is the results of that data-driven model. We've got a training set and a validation set. And it appears to have reasonable skill over this very short one-day time period in terms of the temperature projections. So what we've then done is gone in and interrogated this to try and understand, whether or not those data-driven projections are physically meaningful. And so we've done a set of things. First of all, we just looked at the coefficients associated with all those different input variables that we put in, and that's shown in the top image on the left-hand side. And you can see what stands out in terms of the linear terms is the density. The density is shown as being the most important coefficient in terms of what's most used in this data-driven approach. But we've also looked at experiments where we've withheld certain input variables and looked to see the impact of that. And actually, in the withholding experiments, the impact of withholding the density is actually quite small. And that's because actually, if you withhold the density, then actually instead the temperature and salinity, which are closely related to the density, take up the role of density in the data-driven approach. And in the withholding experiments, it's actually the currents that have the greatest impact, which in itself is relatively physically meaningful because the currents are critically important both for the advective and the diffusive processes that are critical to driving that overturning circulation, which, as I described, is the thing that is most impactful for determining that temperature change. So in a sense, the results of this are all very physically meaningful. And you can see the image that's on the bottom right-hand side there is the additional errors that you get if you withhold the currents. Again, you can see that pattern in terms of the red and places where you see those greatest errors where it's clearly not creating that temperature change associated with the overturning circulation. So that's the oceanographic example. Just very quickly, a final example of yet another different type of approach that we've been doing is looking at hydrological forecasting, looking at flood forecasting associated with heavy rainfall. And here we've been looking at whether or not we can create alternatives to hydrological models where we use a data-driven approach that contains a set of hydrological and climate variables. One of the most important is the rainfall over a previous period of time, the antecedent rainfall over a period of time, because it's not just the immediate rainfall on a particular day, but how that rainfall is built up over a period of time, and using that to try and, in different river catchments, project the future flow of those rivers. And you can just see the results of a data-driven approach that we've got there, which is showing a reasonable skill. So I won't go into more details other than to say that's another area of interest, because otherwise I'm getting short on time. The very last thing that I wanted just to highlight is coming back to where I started, which is what we'd really like to start doing is go the extra stage. So I've been describing how we're looking in different ways at different climate-related forecasting, but what we'd really like to do is extend further and to look at the implications of those climate-related risks. So implications, whether it's on energy systems, or whether it's on urban resilience, or whether it's on health. And in that case, we're interested in understanding whether or not we can also be using data-driven approaches to do that mapping between what the socioeconomic impacts are and what the climate-related variables are. Can we create, if you like, a damage function, data-driven damage function that allows us to map the climate-related impacts into socioeconomic impacts? And that's something that we've done some work on in certain instances. One of the real challenges is finding enough data in order to be able to undertake that sort of analysis. So let me just summarize then very simply to say that it's still early days in terms of the work that we've been doing, but it's clear that data-driven approaches across a wide range of climate-related problems are starting to show great promise in terms of predictive capability. And I think we're increasingly starting to understand where there are opportunities for using machine learning approaches in a very wide range of different problems. So thank you very much.